Greetings, welcome to the 7th session of the Science Settle of Frequencies meeting. I'm Resmi joining from Thiruvananthapuram in India. This session is on Milky Way's galaxies and clusters. Our first speaker is Sarah White, who is going to talk to us about the 2020 view of the AGN world. Sarah, may I request you to start sharing the screen? Meanwhile, to the participants, you could type your questions in the Q&A box, and we will pass it on to the speaker at the end. Sarah, you have 25 minutes for the talk and 5 minutes for the question and answer session. Over to you.
Oops.
Sarah?
Yes, can you hear?
Yes, yeah, sure, we can hear you.
Okay, but you've lost the screen
It
share
looks
now.
like the screen share is lost, yeah, that's right.
Yeah, okay, let me try that again, sorry. Literally just had it.
Yes, but it's not full screen. Yeah, no, it's fine. Now it's fine.
And you can hear me at the same time?
Yes, yes, everything is fine.
Okay, great, thank you. All right. Yes, sorry for that slight delay. Thank you very much to the organizers for inviting me to talk about my favorite subject, which is active galactic nuclei, or AGN. And I know it's been a very difficult year, but whilst Mother Earth has been taking matters into her own hands, there have been a number of really exciting studies in the AGN world. So I'll start my talk providing some context for this area of work and mostly highlight papers through the year that also use different telescopes. As I've been asked, although this is a Science at Low Frequencies meeting, we do want to emphasize that we combine all of this information with data using other telescopes. And also towards the end, I'll just highlight a few ideas for where we could go next. So to start off, what do I mean by an AGN, active galactic nucleus? So the idea is that we have a supermassive black hole at the center of the galaxy, and as material or gas is falling onto that black hole, it produces a large amount of emission over a wide wavelength range. And in some of the cases, we have the production of these very powerful radio jets as illustrated here. So surrounding the supermassive black hole at the center, we usually get this accretion disk forming, and beyond that, a ring, also known as a dusty torus. Now, there's a few other labels I just wanted to go over just for a moment. So blazar being when we are looking down the radio jet axis. And then we have this idea of a quasar, which is where we're off axis, but we're still usually looking towards the center where the accretion disk is. But in some cases, if we have dust along that line of sight, then we would have a dust obscured quasar. So that's just something to bear in mind. The level of dust obscuration can tell you what type of quasar you're looking at. And then we also have the name radio galaxy, which in this illustration implies that we're looking at it side on, but also notes that, well, radio loud quasars are really a type of radio galaxy also. So it depends on your favorite flavors, I guess. So why do we want to study these radio jets? Well, ultimately, we want to understand how they impact their surroundings. How does that supermassive black hole at the center influence its host galaxy? And this is a really nice composite image that illustrates the necessity to view these objects at multiple frequencies, and indeed that may be to use multiple telescopes. So on the left-hand side, we can see how LOFAR allows us to pick up this really beautiful, complex, extended emission associated with M87, also known as Virgo A. And you can pick out all this very nice structure in these lobes. And then as we move to higher frequencies, remembering that usually we have the resolution scaling with frequency, that allows us to zoom in and we can in more detail look at how those jets are interacting with their surroundings. And then going to higher resolution still, we can make use of very long baseline interferometry. So really pick out the structure of those jets and learn more about the physics. So how are they interacting with the surrounding medium, but also what are they composed of even? And then, of course, this brings us to this very nice image using the Event Horizon Telescope, which was the first image of the accretion disk surrounding a supermassive black hole. So trying to tie this back into how AGN fits in the general galaxy evolution context, the two most important processes to bear in mind is star formation and black hole accretion, of course, both producing radio emission. And both of these processes appear to peak around redshift 2. They follow a similar trajectory over cosmic time. And that appears to indicate that those two processes are indeed interconnected, that there's some kind of feedback mechanisms that allows one to kind of talk to the other. But the other explanation could be that there's a common reservoir of gas that fuels both the star formation and black hole accretion. So this is also an area that's up for debate. How important are these feedback processes in the scheme of things? At the bottom, we also have an image of the radio jets impacting, overlaid onto a grayscale image, impacting on a molecular cloud, triggering its collapse and subsequent star formation. But in other cases, you may have those jets impacting on a cloud and completely dispersing the gas and preventing stars from forming in the first place. So that's another area in which we need further investigation. And then how does all of this tie in with the apparent co-evolution of the supermassive black hole and the velocity dispersion of the bulge? And this is something seen for a wide variety of galaxy types. Now remember that black hole is only a few milliparsecs across, and yet it's able to have an influence over 100 kiloparsec scales. Now, in terms of low frequency observations, there are a number of benefits for why we want to use these for observing active galaxies. Now, first and foremost, by going to low frequencies and doing a selection there, it means we can create an active galaxy sample that doesn't have an orientation bias. And that comes down to this idea of relativistic beaming or Doppler boosting. Because at higher frequencies, the radio jet that's pointed towards us would have its flux density artificially increased, whereas the radio jet pointing away from us has its flux density decreased. And so doing a selection at higher frequencies, you then encounter a bias towards these either core-dominated sources or systems where the radio jet axis is close to the line of sight. But doing the selection at low frequencies means that we can avoid that, since low frequency emission is dominated by those lobes and is unaffected by this phenomenon of relativistic beaming. It also allows us to get better constraints of the broadband radio spectrum, and I'll come back more onto that in the next slide. And also to note that as radio emission ages, it moves to lower frequencies. And that means we can get a much better census of the different ages of the AGN population and better understand the life cycle. How long are these AGN actually interacting with their surroundings, and also their intermittent behavior, switching on and off again. So to illustrate this a bit more, and also to highlight why we need to do multi-frequency analysis, is that we actually use spectral age models to determine, well, what is the age of this radio source? And as you can see here, we have the power law function that would be just the injected electrons, giving you our standard synchrotron emission. But over time, we have a depletion of these higher, if it switches off, we have a depletion of these higher energy electrons. We lose energy through synchrotron radiation, inverse Compton scattering, and also adiabatic expansion. As a result, the radio spectrum takes on a more and more curved appearance with age, hence it going in this direction. And just to highlight that the color scheme that's used here is actually the opposite way around to the color maps that are used for these illustrations along the top. So when we have this curved appearance, that allows us to distinguish between these different spectral age models. And of course, having a wider bandwidth means that you can do that discrimination more easily. Now, of course, as we know, the MWA has very excellent spectral coverage, and that gives us 20 flux density measurements at low frequencies, allowing us to very nicely constrain that part of the spectrum. Now, if we focus, for example, in the Green-Podjansky sample, which is a compilation of the brightest sources in the southern sky, let's focus on the doubles here. And the vertical line is placed at the canonical value of -0.7, that's being the spectral index. You can already see that there's several steep spectrum sources. And so it's likely that these are all at different ages, and that would be already in itself a very interesting subset to investigate. Now we can, of course, what would be very exciting is to take this further by combining this spectral coverage with spatial resolution. And here are just a couple of examples of work that has come out this year. So in the top right, we have this giant radio galaxy. So with GLEAM giving us information at low frequencies, but also follow-up data, for example, with the Australia Telescope Compact Array. And what we have here is the typical flat spectral emission that you'll get associated with the core, whereas we have the steep spectral emission associated with the two lobes. And also just come out is some nice new work, beautiful pictures using the combination of LOFAR and Aperitif, giving us very nice spectral index maps between those two frequencies, so 144 megahertz and 1.4. And as you can see, this here, the radio core has your typical flat spectral emission. This color scale, the numbers are the opposite sign for the spectral index given here. But you can see the power that spectral index information gives us in also identifying the core and helping host galaxy identifications. So what would be really wonderful is if we could combine the excellent spectral information from the MWA with excellent spatial resolution from LOFAR over an overlapping region and truly truly get the best of both worlds. I look forward to such a project. Now, taking that spectral index work a bit further, there's also this work by Marissa Brienza, and she's going to talk on, I believe, a different system at this conference, but previous work earlier this year, if we focus, this is another spectral index map, but between 1.4 and 5 gigahertz. And if we go along these directions, we can, with the spatial information, we can actually see how the spectral index varies across the map. These two radio lobes are actually coinciding with these kind of cavities that we see in the X-ray. And this just is to illustrate that the jets are kind of inflating bubbles. and dispersing the medium, and that is also transferring energy to the surroundings. So we can use those cavities to also get an idea of how much energy is being deposited, because in the end we want to know how is these jets or outflows actually affecting the host galaxy and any star formation. And this image just reminded me of previous work, also a very nice radio galaxy, and which is carving out these kind of shells as described in this image here. Now, taking this another step further, we also find that we get these extended structures in radio quiet sources. So this isn't new this year. There's been previous work by Baldi et al. In 2018, but it's still very exciting to me. There's these observations using VLA at 22 gigahertz, and this is 1 arcsecond resolution. And for this sample of nearby AGN, which are deemed to be radio quiet, they pick out these very nice kiloparsec scale radio structures. And on the right, I'll walk you through this plot, so don't worry. The gray plot dots here refers to the star formation mass main sequence. So this is where we'd expect the star forming galaxies to lie along. And you note that the sources in their sample, so that these data points here, many of them lying below that star formation main sequence. So this is an indication that there's some process going on that's actually suppressing the star formation in these sources. So that's what we typically refer to as quenching. Now the orange data points, those are sources where other radio information is telling them, oh, actually, there is definitely extended, there are radio jets present. But for the red data points, it's still uncertain what is actually giving rise to this morphology. And so this connects us to, well, how do radio quiet AGN fit into the bigger picture? So there was a very nice review last year, and this is a nice summary plot. For this work, we're just going to focus on whether this radio emission, this structure, is due to outflows or wind connected to the accretion disk, or whether it's connected to a young radio jet. And what's nice in this work by Smith et al. Is that they calculate multiple energy estimates using this jet idea and also using the idea of winds. And they compare these energy estimates to the energy you'd need to actually remove gas from that gravitational potential well, or to transfer energy to the gas clouds that are rotating around. Since if we can give them enough energy to disperse, then those clouds won't be able to collapse and form stars. So those are like two criteria that they use. And what's interesting is that it seems that the wind explanation could actually suppress the star formation in these galaxies, and the jet argument is actually not quite enough. So earlier in the previous session, you will have seen Christina Nyland's talk, which is a very exciting piece of work. For those who haven't seen it, this is just kind of a one-slide summary. So based on a comparison of the first survey at 1.4 gigahertz, done back mostly in the 90s, and the new VLAS survey, noticing that some quasars have gone from being radio quiet in the original survey to suddenly becoming, over decades, becoming radio loud quasars. And just to focus on this orange strip here, so this is the L band now, we want to do, of course, a like-for-like comparison, even though it's quite clear that between L and S band, yes, they are indeed very well separated. But the follow-up multi-band observations nicely marks out this spectral shape and confirming that, yes, this is like a real change in the radio properties of these sources. So this also connects nicely to the work by Kat Ross, so also a talk you would have seen earlier. Her paper has just been accepted this week. And the idea is that we want to use, have a way of quantifying the variability in the spectral shape, as well as just the usual way in terms of a single band. So this is just to extend it a bit further. And then, of course, it's kind of obvious from these plots that these are peak spectrum sources, but indeed they do sit in this part of the spectral color diagram.
Sarah, this is just a 5-minute warning.
Oh gosh, okay. Thank you. So just to emphasize that this idea of going from radio quiet to radio loud isn't, it's not completely new. It's, there's also been some simulations in the past. The idea that we have a star-forming galaxy that has had some kind of infall onto the supermassive black hole, increasing its accretion rate, going through a radio quiet phase, and then at a later stage having this radio loud phase. And this is just one simulation that Mancuso et al. Then tested using a sample of radio quiet quasars. I didn't have anything to do with this, I wasn't the referee, but this work did do a very careful separation of the radio emission into the accretion component and the star formation component. And so it follows those evolution tracks, but of course more work is needed. This is a sample of optically selected quasars, all at redshift 1. And tying into this, do look out for John McKean's talk, doing that very careful separation between star formation and AGN. Now, along the same lines of simulations, there's also been the SIMBA simulations that came out last year, because we want to make sure we incorporate radio information in cosmological simulations, not just which are mostly focused towards optical surveys and those comparisons. We want to also incorporate information of how do we actually get these radio jets being constructed, and also how do they influence their surroundings. And what's nice is that with their work, so this is a recent paper by Thomas et al., with very little tweaking, they kind of naturally, they get these radioluminosity functions that kind of fall out with the star-forming galaxies, indeed showing good agreement with star formation radioluminosity functions by Mouch Sadler, and then also producing the AGN radioluminosity function. And they take it a step further by splitting their radio galaxies into HERGs and LERGs. So this is seminal work by Bess and Heckman, the idea being that we have these two different ways of accreting onto the supermassive black hole. If it's taking place very efficiently, we have these high excitation sources. And if it's taking place inefficiently, also known as Bondi accretion, we have these low excitation radio galaxies. And for the SIMBA simulations, they use that separation and use different subgrid physics to prescribe how is the accretion taking place onto the black hole, and keep that label for when they analyze the results. And so this is what happens when we then look at the radioluminosity functions again, but separated into the HERGs and LERGs. Now, the way that they do the prescription actually means that for the very low accretion rate sources, they're able to produce these sources, the LERGs, very well and get good agreement with the AGN luminosity function. But it's not quite clear what's happening for the higher accretion rate sources, because they also note in their paper that they pick up, I think it was 1 AGN between an accretion rate, this is the Eddington fraction, between 2 and 10%, whereas our observations appear to indicate that there should be many more sources at higher accretion rates. So it's not quite clear what's happening. So, but lots of interesting discrepancies that we can investigate further with future telescopes. And so this was just to flag up, of course, the three magic words, square kilometer array. But until that comes online, of course, we have this wonderful array of telescopes that we can make use of in the meantime. And also just to highlight that in the Southern Hemisphere, we also have the MWA and the Australia Telescope Compact Array to do follow-up observations. Now, just picking up on two of these telescopes shown here, the JBLA and ALMA, some recent work was looking at the orientation of the molecular gas around these radio jets for a sample of radio galaxies. And this was just a proof of concept study, but they plan to use this method. So they also combine it with information on the presence of dust and the orientation modeling that allows them to pick up, well, how inclined is the radio jet axis with respect to the molecular gas surrounding it. But my final couple of minutes, I just want to go through, of course, my favorite telescope being MeerKAT. So this week we have the SARO National Conference. And for those who don't know, MeerKAT is in the Karoo Desert. And we have a great spread of baselines, which means that we simultaneously pick up very diffuse emission, but also the longer baselines, of course, gives us good spatial resolution. And in a single 1.5 degree across field of view, we pick up all sorts of beautiful structures. Even if you're only looking at the source at the center, we pick up these wonderful radio galaxies in lobes that we wouldn't have been able to detect before because they were just way, way below the previous limits. And of course, this talk couldn't be complete with some of these beautiful images of radio galaxies with MeerKAT. So Fornax-A, we're now seeing evidence of episodic activity. These never seen before collimated synchrotron threads connecting these two lobes, which is just quite mind-blowing when I first saw that. We talk about a square kilometer array allowing us to discover the unknown unknowns, and we're already kind of doing that with MeerKAT. And of course, this beautiful X-shaped radio galaxy where the filamentary structure within the lobes allows us to provide evidence for the backflow hypothesis, being that the radio jets emanated in that kind of north-south direction, energized the plasma, which flowed back towards the center, and then got deflected by the gas reservoir, creating these wings in the east-west direction. And so my final slide, this year, we may have been locked up, but we've also been very, very busy. Want to emphasize that we do need to do this multi-frequency analysis if we want to understand the full life cycle of AGN. And you may have noticed in the talk, I've gone backwards and forwards between radio quiet and radio loud work, because in the end, they are active galaxies, and these galaxies all have a supermassive black hole at the center. And so where do you place the dividing line between the two? So if you have questions about the definitions, please feel free to ask those. We're still, of course, limited in the resolution, both for our observations and simulations. Whilst we need a mixture of single source studies and also population studies together to propel our physics understanding forwards, the reason I've listed these surveys here is just as a thank you to the hard work that goes into them, because it allows so many science cases to reap the rewards. Thank you very much.
Thank you, Sarah. That's a very detailed review. We will have a very quick question. We have nothing in the Q&A, but we have George Mealy. May I ask George to talk now?
Yes, well, thank you, Sarah, for a really nice talk. I have one comment and two questions. The comment is about the histogram you showed of the spectral index distributions. I think one has to be very careful when one lumps all of the sources together, because as you probably know, there's a correlation between spectral index and redshift. And as you go to higher redshift, you're also going to a different emission frequency. So that's all lumped in this type of correlation, this type of histogram. Yes. So I think you have to be rather careful in interpreting it.
And also this histogram is actually only for 76% of the sources. There are still sources that are not fit by a power law because the spectral curvature is to such a degree that...
Yes, and as you go out to higher redshift, you're going to a different part of the spectral index. So that's all lumped in and mushed up in this type of correlation.
George, excuse me, is it okay? I'm sorry, we have slightly overshot in time.
Oh, sure. Oh, go ahead.
I'm sorry.
No problem.
So we can have the continued discussion in Slack, and is that okay?
Yeah, we'll do it afterwards. Yeah.
Thank you. Thank you, Sarah, once again.
Sorry for the technical difficulties at the start.
No problem. Our next speaker is Chris Rosselli, who is going to speak to us about low frequency polarimetry with next generation aperture arrays. Over to you, Chris. Could you please start sharing your screen?
Cool, thanks. Hopefully you all can hear me and see my slides. Wicked. I'm gonna assume that you can unless anyone says otherwise. Yes, thanks for inviting me to talk about polarimetry. Those of you who know me will know that I have a fairly heavy MWA bias when it comes to this kind of work. But for this review talk, I have done my best to make it a little bit, to adjust the balance a little bit and include some of the ongoing work with LOFAR. So my talk is largely divided into three sections. There's a bit of background, the motivation underlying physics. I'll tell you, why we do what we do, how we do it, what we can learn. The bulk of my talk will be devoted to presenting results from low frequency polarization surveys. And finally, I'm going to wrap up with a little bit of a look to the future and tell you a couple of the main lessons that we've learned that hopefully we will take forward to the SKA era. So first things first, a little bit of background, polarimetry, what, why, and how. I like to start off with the why, the motivation for why we do this kind of work. If you're a big picture kind of person, polarimetry is really cool because it can tell us about the origins of cosmic magnetism. We can test these various models of how magnetic fields arose in the universe, and we can then study how the magnetic fields have evolved over the cosmic time. If you're a medium picture kind of person, then polarimetry is cool because it allows us to understand sort of galactic and intergalactic magnetic fields and magnetic fields in clusters in the cosmic web. And if you're a slightly smaller picture kind of person, that's totally fine. Your science is your science. And polarimetry is cool because it can tell us about the magnetoionic properties of all types of galaxies and pulsars. And in these fields, polarimetry is really important because magnetic fields have a big impact on galaxy evolution, feedback, star formation, and all of these things help regulate the chemical enrichment of the universe. So really, polarimetry is cool because it provides a window into pretty much all areas of astrophysics. So you should be interested. The how is this technique known as Faraday rotation measure synthesis, or RM synthesis. So picture a scenario a bit like this. You have some radio galaxy off in the universe, happily radiating away, and it's emitting radio waves. These travel out through the universe, and at some point, they encounter a cloud or some kind of region of magnetized plasma, whether that's in the external ambient medium or in a cluster or whatever. These plasmas are birefringent, so effectively each handedness, because you can decompose a linear polarization wave into two circular polarization waves, each handedness effectively experiences a different refractive index, and so the plane of polarization rotates. And that is what we detect with our radio telescope here on Earth. Now, what we measure is this frequency-dependent polarization angle, which is some function of the intrinsic polarization angle at the source, and this quantity Rm dot lambda squared. This Rm is your rotation measure, which is this integral quantity that looks a bit scary, but it's totally fine, because what it really tells us is that the amount of rotation depends on essentially two quantities. You've got your free electron density and the line of sight magnetic field strength. So the theory is what we want to do really with these large scale studies is to get RMs for all kinds of sources all across the sky, and then we can use that to reconstruct cosmic magnetic fields in the universe. And that's the theory behind these RM grid studies. And there have been a lot of work going into these, mainly at higher frequencies, but we're starting to get there at lower frequencies, and I'll come on to that a bit later. There's three key parameters that are important for RM synthesis, and I don't normally like to show equations, but this is important for context. Now, they're governed by these three equations, and I've removed some constants to make your life easier as the viewer. But essentially, what this tells us is that our resolution in RM space goes as your wavelength squared difference across your bandwidth. The maximum scale you can recover goes as 1 over your shortest wavelength squared. And the maximum RM you can recover goes as your lambda squared difference across your channels. Now, we're at long wavelength, sort of greater than 1 meter. So we naturally get high RM resolution. And the kind of aperture synthesis analogy to RM synthesis here is that we have an interferometer with long baselines. Likewise, our maximum scale is small because lambda is greater than 1, so the denominator is large. And the analogy is that essentially we're sort of missing short spacings. And I don't really have an aperture synthesis analogy for the maximum RM you can detect, but the nutshell is that we need fine channelization to detect high RMs. And with a survey like POGS, which is has been my pet project over the last couple of years, which covers the frequency range 170 to 231 megahertz, we have an RM resolution of about 3 radians per square meter, but we can only detect things that are up to about 2 radians per square meter thick in RM space. So essentially, if you've only got low frequency data, you're only really sensitive to unresolved in Faraday space structures. And these are things that in the lingo we call Faraday thin. There are some caveats to that, but for simplicity, just, that is the situation largely. What we've done previously, historic RM surveys have typically used higher frequency data from the MVSS catalog, which have sort of more than 40,000 RMs above DEC minus 40. That's pretty good. But below DEC minus 40, there are less than 1,000 RMs. That's not so good. And these are usually largely inhomogeneous based on samples from different surveys, which have different sensitivity, different frequency coverage. So they have different RM properties, different spatial resolution. So it's not bad, but there is some intrinsic bias in there. So that's also not so great. In the imminent future, there's going to be the POSSUM survey using ASCAP, which is broadband, it's highly sensitive, and it's homogeneous in terms of resolution and frequency coverage, etc. And it's also really cool because it goes towards filling this southern hole, which is really important. But what about low frequencies? This is where I'm going to be going on to for the remainder of my talk. I'm going to be telling you what we've learned from the MWA and LOFAR. In terms of a brief history, here are a bunch of papers that you can look at from the last 7 years. I'm not going to go into the important results of each of them, but the take-home message from this is that over the last 7 years, we've gone from the state of the art being sort of having one source per field to the state of the art being where we have many hundreds to many thousands of sources across large area surveys. State of the art with the MWA has been my work with POGS, which is the polarization component of GLEAM. And state of the art with LOFAR is just mind-blowingly awesome. You can see some of the vital statistics there on the left. They're very different in terms of resolution and marginally different in terms of sky area, and lots is finding heaps of sources. But this is essentially the all-sky distribution we got with POGS, where circles are extragalactic sources and stars are known pulsars. And then if you throw in the first several hundred of LOFAR sources, you can see we're starting to get to this stage where we're building out the sky coverage, which is really, really cool, because this has not been done before at low frequencies. And some of the eagle-eyed among you in the audience may have spotted it, but just to highlight this for everyone's benefit, we are into a period now where we have overlap, which is really cool because we can start doing long wavelength polarization science with LOFAR and the MWA, which is super cool. Focusing a bit more on POGS and such, generally it kind of looks like we have a relatively non-uniform surface density. If you look at the distribution of sources, it kind of looks like they tend to avoid regions where there's high foregrounds, but we also see that high RM sources tend to be associated with, or rather have a line of sight that passes through regions of ionized emission, like H2 regions. And here's a few that I've highlighted here, overlaid on the ThinkBiner H-alpha map. But unfortunately, the surface density was too low to really statistically say that the distribution is clustered, but it kind of vaguely looks like it that way. And further work with phase 2 will be really interesting in that regard. We can look at the bulk spectral properties, and this is where I start to fold in some of the LOFAR work. This is a histogram plot from a paper by Vijay Mahatma and collaborators that is currently in review. So Vijay, thanks for sharing that with me. This is really quite a key result because it shows that sources that are detected in polarization by both LOFAR and the MBSS are preferentially steep spectrum, whereas those that are only detected in polarization with the MBSS are marginally flatter spectrum. Following discussion with Vijay, I repeated the same analysis using the available POGS data. And the trend is much more marginal, but we do see a slight hint of a shift in the same kind of direction. Now, there is a much greater resolution mismatch between POGS and the MBSS. So take that POGS histogram with a bit of a grain of salt, but know that phase 2 polarimetry with the MWA will allow us to investigate this much further because we'll be able to match resolution with the MBSS, which is awesome. Polarization and spectral complexity. This is where things get a bit interesting. We have 329 sources in POGS, which have counterparts at higher frequency. And what I'm plotting here is the RM we measure at 200 megahertz on the y-axis versus the higher frequency, whether that's 1.4 gigahertz or 2.1 gigahertz on the x-axis. And what you'll see is we have a number, they generally follow a really good one-to-one relation, but we have a number of outliers. And one of the natural things that we want to do is learn what causes these outliers. There are two principal explanations that spring to mind, one of which is that we may have multiple polarization components with different spectral properties. So one RM dominates at low frequency, one dominates at high frequency. And the other one of those is simply that these could be time variable, which is something that has been seen in a number of papers. So let's look at the spectral properties of these sources a bit. We have 10 sources in common with Joe Callingham's Gleam Peak Spectrum Source Catalogue, which was mentioned earlier this morning by Kat Ross. And those have been highlighted here in red. So you can see that a number of these outliers do have interesting complex spectral properties because they are peak spectrum. But let's look at a number of the other outliers. These two here are relatively boring power laws. And note that the dashed lines I'm showing on these plots are not actual fits, they're just kind of chi by eye. But the one on the right may exhibit some signs of variability. Alternatively, there may just be some calibration issues. So those don't exhibit any real interesting spectral properties. This source over here, on the other hand, exhibits a more interesting concave looking spectrum. So that's something that's interesting. And the clearest outlier over here, I just wanted to show this spectrum because it's really, really peaked. This is the most obvious outlier. So what can we take from this? Well, we have a number of sources that show complex spectral properties and are clear outliers in the RM plane. Some of them don't. And if you want to, look at the vital statistics between POGS and peak spectrum source catalog, we have 3 sources that are pretty good outliers. One has a completely consistent RM at low and high frequencies, and 5 of them don't have a high frequency RM. So that's unfortunate. We can't really tell there. But we do have kind of hints that there is some, maybe relation is a poor word, but perhaps there is some common property between these sources. So this may suggest that these RM differences may be being driven by different complex spectral properties. We need an increased sample size. Lots of polarization and POSM and follow-up observations are going to be really key to understanding and unlocking this. And there is some overlap with Cat Ross's sample. So some of these sources are variable in continuum and may have different different high and low frequency RMs. So there may be a link there. Stay tuned. Now, looking at bulk properties of the AGN population, this is getting diving a bit more into a statistical comparison. Tessa Wernström did some great work last year using physical pairs of polarized sources where you have 2 polarized components that are associated with like one radio galaxy. An example of which from POGS is shown on the right here, where you have one radio galaxy with 2 polarized hotspots, compared to random pairs of not physically associated but spatially nearby polarized sources to do a statistical detection of cosmic magnetic fields. Shane O'Sullivan did some similar work with a subset of low-FAR sources at 150 megahertz looking at the structure function. And unfortunately, the surface density we see with POGS is too low for a meaningful comparison of random pairs, but we can start to look at how POGS contributes to the physical pairs. And that's what you see in this plot on the right. Low-FAR sources from various different low-FAR catalogues are shown in blue, and our POGS physical pairs are shown in black. And the 1.4 gigahertz RMs are shown in orange. So what we're showing here is delta RM squared. So this is the squared RM difference between 2 polarized components in the same source, so 2 polarized hotspots, for example, as a function of angular separation. And the binned averages for each sample are shown in the solid lines. And what we see is that at low frequency, we have roughly an order of magnitude lower delta RM squared difference compared to high frequencies. And we can, if you're thinking back to earlier, the earlier equations I showed, this is likely due to difference in properties of the host environments themselves between the sources detected at low frequency and the sources also detected at high frequency. And the just thousands of sources that will be detected by the low-FAR polarization component of LOTS and phase 2 NWA will provide big constraining power in this regard. So again, stay tuned, it's only going to get more awesome. As a side note, I couldn't resist throwing in a bit of a plug for the known PULSAR catalog, because I've seen a lot of chat blowing up on the PULSAR channel of this Slack. As part of POGS, what we did was a search for known pulsars using the ATNF PULSAR catalog. We detected 33, which is cool. You can see the RMs are pretty much completely consistent with previous studies. Although again, we're at long wavelengths, so we get a median of 40% better precision compared to the already quite precise RMs in the ATNF PULSAR catalog. And we have 11 pulsars for which we make the first low frequency detection. So these things weren't detected in gleam continuum, but they were detected in gleam polarization, showing that we can achieve better sensitivity in polarization. And looking at a histogram of the polarization fraction, this pi quantity, we see actually a curious bimodal distribution in terms of the polarization fraction. We ran a 1-sample KS test, and the probability of these being drawn from the same population is extremely small. So we can confidently reject, we can confidently say that we do have a bimodal distribution. But there are no common traits between these two populations. They have a mix of DMs, they have a mix of spin period, they have a mix of spectral index, and various other quantities. So that's something to be followed up, again, with a larger sample size. And as part of this, we also have 4 new PULSAR candidates that are being followed up with observations with PARCS and the MWA voltage capture system. So 4 new candidates from among our nominally extragalactic source population that look like they could be pulsars. So again, stay tuned. Now, this kind of brings me, gives me a little bit of a segue into near future work with POGS-X, which is the polarization component of the GLEAM-X survey. So here is one of the POGS sources, POGS-J0636-2036, perhaps more commonly known as the exclamation mark source, because it kind of looks like an exclamation mark. The southern hotspot of this thing was the brightest polarized source, the brightest extragalactic polarized source in our POGS catalog, with a polarized flux density of 1.2 Janskis at 200 megahertz, which is booming. And we also detected another polarized component associated with the northern hotspot of this radio galaxy. Now, moving to phase 2 polarimetry, and here is an image kindly provided by Zhang Zhang, who is a postdoc at CSIRO. She's done some excellent work, completely reinventing the polarization pipeline for phase 2 data, in conjunction with the hard effort put in by Natasha Hurley-Walker and a few other people. But essentially what we see is with these phase 2 data, with the MWA long baselines, we get 3 main polarized components, 3 main largely compact components, plus resolved emission. So there's this, and I should note that the 2 main polarized components associated with the hotspots are detected at the same RM we measure with POGS, so that's important validation. But it's really cool to see the sensitivity gain and these extra components emerging. And really we've got about a factor 3 improvement in resolution between POGS and POGS-X. Now that we're able to achieve this 45 arcsecond resolution, this has been a real game change. Not just the resolution change, but also improvement in calibration quality, improvement in beam models. We're going to detect heaps more sources. But it's more complicated because one thing we did with POGS was essentially we just kind of treated everything as a point source, because we've got like anywhere between 3 and 7 arc minute resolution with the phase 1 data that we had. Whereas at 45 arcseconds, you can't just treat everything as a point source. So there's some rethinking that is going on.
Chris, this is a 4-minute warning.
4-minute warning, fantastic. Thank you. This brings me nicely, perfect timingly, onto the last segment of my talk. What lessons can we take forward to the SKA era? There are many, many lessons that have been learned as part of this, and these should absolutely be documented somewhere so they're not forgotten. And we don't have to relearn these lessons 5-10 years from now. But I've picked 2 that are probably key in my opinion. Firstly, prepare for the deluge of big data. We know that the SKA is going to be big data, but I want to exemplify just how much big data we're going to have to deal with SKA, with SKA low, but based on my set of experiences with POGS. And I wanted to throw in an RM cube here. You'll see a few things that come through. You'll see diffuse polarized galactic foregrounds sweeping through, largely in this kind of pink region on the right. You'll see a couple of real sources pop in every now and then. And when the whole thing lights up like a Christmas tree, that is instrumental leakage. Now, this was 1 epoch of 1 deck strip, so it's only 2,400 square degrees of sky. It's a subset of our RM range that we're sensitive to. And this is a 220 gigabyte FITS file. So I could just about open it up in KViz on a high memory node of the CSIRO high performance computing resources. For POGS-2, we cover a larger frequency range at 40 kilohertz channel resolution, and we have 28 quanta of observing data. Per quantum, we have a number of terabytes of intermediate files, and then the final RM cube we have to analyze is 1.5 terabytes per polarization on disk space. That's a scary number because you need massive compute resources just to get here in terms of hours and memory. Analysis is tricky because 3D source finding is a pain, and no source finding algorithms that I was aware of at the time are able to handle the kind of noise statistics that polarization noise typically exhibits. One of the partial solutions, and this is what we did for POGS, was to leverage the total intensity catalogues. We looked for polarized sources at the location of known continuum sources. But things get more difficult where you have resolved structure and can no longer treat everything as a point source. And if you're interested in galactic foreground, and we see sparsely sampled bits of it here, and Anna has a talk a little bit later in the same session looking at foreground in more detail with LOFAR. If galactic foreground is your jam, then this is going to be tricky. And this is only with sort of arc minute resolution. Once we get down to phase 2 MWA resolution, this is only going to be an order of magnitude worse again. So suddenly your RM cubes are bonkers big. And then and that means, we have petabyte scale imaging requirements now, and SKA-low is going to be another order of magnitude more complicated. So we're going to have to think about this really, really hard. Lesson number 2 is that a good beam model saves an awful lot of post-processing. So what you're seeing here are the RM spectra for the southern dot of the exclamation mark source in phase 1 and phase 2 on the bottom, phase 1 on the top, phase 2 on the bottom, courtesy of Zhang. Now, what you can see, the main region to focus on is this kind of low RM region near 0. And you can see the improvement in the residual kind of rubbish in that low RM region. This is basically due to improvements in the beam model. Those peaks that we saw in phase 1 are trash. Well, trash. It's instrumental leakage. It's not real stuff. And so, this is the best case scenario. But for a source way off zenith, there is much more gnarly leakage in phase 1. So perhaps things will be different in phase 2, but this goes to show that a good beam model saves a lot of post-processing and a lot of manual inspection. If you're looking for peaks in that low RM region, are they real? It's tough to tell. So in wrap up, we are in this region, this time now where we are undergoing a renaissance of low frequency polarimetry. We can get precision RMs for large numbers of sources. We can look at the bulk properties of these populations, and we can finally do low frequency source counts in polarization, which is cool. There's a lot of physics to be explored using low and high frequency data and high resolution data. It's only going to get better with phase 2 of the MWA giving us this broad spectral coverage at reasonably high resolution, and suddenly a lot of things become resolved. The LOFAR high resolution data at sort of 6 arc seconds will be epic, but it's also an epic challenge. And finally, with the MWA and LOFAR, we'll be able to construct the first low frequency precision all sky RM grid, which is extremely cool. And moving to the SKA era is going to be a challenge. Big data is exacerbated, calibration is important, and let's try not to have to relearn the same lessons. And I will stop there and say thanks for listening and take questions.
Thank you, Chris. That was very exciting. Over to the questions. We have one question from Alec Thompson. I'll just read it out. Are there alternative approaches we can take to data processing? Do we need to do RM synth on the whole sky? Could we do spike racks cell cutouts for compact sources?
Ooh, good question, Alec. Thank you. And thanks for measuring spice racks. Yes, there is some, now with phase 2 data processing, there's been a lot of work going on to automate the data processing workflow, which is extremely cool. Tim Galvin and Zhang and Natasha and various people in the GleamX team have been working really hard on automating that. For compact sources, absolutely, we could totally do a spice rack style thing. It's tricky if you want to look at diffuse foregrounds type stuff. But yes, for compact or compact-ish sources, we could totally do cutouts. And that's probably going to be one of the ways we have to go for that.
I guess all the questions from Alec is answered. He had 3 questions, I guess. Are there other questions, or the attendees can also raise hand using the raise hand function? Any more questions? We can probably take one more one or two more, maybe. Yeah, Sharaz Tuadi is asking, when will the phase 2 MWA is expected?
Ooh, so phase 2 MWA, the hardware has been on the ground for a while now, and the data processing has really ramped up this year. There's been a lot of stuff to reinvent, and big credit to Zhang and collaborators for taking the components of the data processing workflow that I was able to get by with using the RTS and reimagining that for the shift in available compute resources. So it's taken a bit of time to get everything together, but we have a really good processing workflow now, and I'm not totally sure when the first results will be out, but it's going to be. There's a lot of stuff going on, and stay tuned because it shouldn't be too long, and it's extremely cool. And I'm happy to go to Slack to chat more about stuff.
Thank you, Chris. If there are no more questions, we could move to the next talk. That's by John McCabe, who is going to speak to us about using gravitational lensing to probe the faintest AGN and radio galaxies. John, you have 17 minutes. I give you a 2-minute alert. Over to you.
Thank you. And good morning, good afternoon, and good evening to everyone who's tuning in today. Yeah, so I'm going to be talking about the faintest low-frequency radio AGN star-forming galaxies that we can currently detect, and we can do that by combining the sensitivity of LOFAR and gravitational lensing. So some of the work I'm going to talk about today.
John, I'm sorry. To me, it looks like the audio is a bit low.
Oh, really? Okay.
Looks, I'm not very sure. At least to me, is.
Try using earphones. So yeah, so the work I'm going to present today has been done in part by some PhD students and bachelor students who were part of our research group in Groningen, mainly done by Hannah Stacey, who's now a postdoc at MP in Garking, Ramon Lucis, who's a bachelor student in Groningen, and Christiana Spingola, who's now a postdoc in Bologna. Sorry, my earphones are all mangled up. Can you hear me a little bit better now?
It's very good.
Okay, sorry about that. Okay, yeah, so we had a really good, interesting introduction error from Sarah, and what I'm talking about is essentially, well, I want to talk a little bit about how we think galaxies form and evolve over cosmic time. So this is a simulation from the illustrious simulation, where you have the optical light, or the stellar light, which we see optical wavelengths, and the gas density, which we see we can probe at millimeter wavelengths. And this is how we expect galaxies form essentially over cosmic time. So you can notice here we have the star formation rate as a function of redshift. And what we expect is that galaxies form hierarchically, i.e. smaller structures merge to form much larger structures. And during this process of galaxy assembly, we find that the amount of gas that's available for star formation increases, but also the merging that we see provides a mechanism for triggering star formation, either through increasing the amount of gases available, or through allowing the gas to collapse via interactions. And you can see as these structures come together, the star formation rates essentially go up to around about 100 to 200 solar masses per year. What you'll also notice is that during the process of merging, we see these moments where the gas is expelled, and we expect that that's due to some form of feedback, whether it be from the AGN, which could potentially be triggered also, or from star formation. And then as we evolve through cosmic time, the star formation rate is expected to come down as we have this final structure at the end, which is a massive elliptical galaxy that we observe today. So that's a very simple those are quite complex simulations. A very simple way of thinking about this is that we start with a dusty star-forming galaxy that forms through a merger. And then during that process, gas is pushed onto the central black hole of the resulting system, and we have what's called a dust-obscured quasar. Now, if there is feedback associated from the AGN or star formation activity, then the gas and dust that's covering our obscured quasar is then cleared, and we see an unobscured quasar. And then as this process evolves, we finally end up with this passive spheroidal galaxy. Now, what we expect is the star formation rate will essentially be the highest in these dusty star-forming galaxies, and will go down as we go through this evolutionary track. And there's been quite a lot of work done, especially with ALMA recently, where there's been with both dusty star-forming galaxies and dust-obscured quasars, where we see evidence of both very large levels of star formation, say order of 1,000 solar masses per year in such objects in both dusty star-forming galaxies and dust-obscured quasars. But really, to understand this full evolutionary phase, we have to kind of try and track these other areas where we're getting to where the star formation rates decrease over cosmic time. Now, in order to do that, we require to improve our sensitivity. And we're doing that using strong gravitational lensing, which is illustrated here in this figure, where we have some intervening mass distribution and some distant galaxy, and then the light is deflected by this intervening mass distribution, distorting the shape of our distant galaxy, but also magnifying it. The result is that we can receive multiple images of the same background object, which we can use to understand the properties of the mass distribution, but we can also infer the properties of objects at high redshift. So I'll be focusing on the latter of those applications in this talk, where we're using the magnification provided by the gravitational lens to say something about the high redshift universe. So how does this work? Well, here's an example where we have a lensing galaxy, and we have 4 images of a background red quasar. This is a 0414 plus 0534 for those that are interested. As you can see, you see the different quasar, you see the different images of the quasar, but also you can see extended arcs which come from the underlying host galaxy. So you can actually also study the stellar populations of these objects in principle. Now, we can use the sensitivity that we get from this magnification to look at objects that otherwise would be too difficult to see, or we can look at objects that are actually below our confusion limit. Just as an example, this is a spectrum we took actually with the Arecibo telescope many years ago, which detected water at very high redshift. And that came from taking all of the light from all of the images and adding it together in a low resolution observation to make this detection. The increased magnifications can clearly reduce your exposure times by essentially the square of the magnification, which really helps with trying to detect these very faint objects. The other application is through the increased angular resolution we get because the lensing stretches our objects. And this is a recent example we have from ALMA. We have this fantastic C2 disk emission from a redshift 4.5-ish dusty star-forming galaxy. And what we do is we have these complex lens modeling procedures, which I'm not going to go into detail, which allow us to take this Einstein ring of a molecular gas and turn it into what the object actually looks like. And of course, this can increase our angular resolutions by factors of 10 to 100 also, because the magnifications are such, which you can imagine would saves a lot of money in terms of trying to build telescopes with longer baselines. So we've been looking at a sample of lens quasars. There are 104 gravitational lens quasars in the initial sample. There's about 250 known quasars, known lens quasars. Now, many of them have come in actually the last few years from wide area surveys with, for example, DES or KIDS. But many of these 104 gravitational lens quasars actually came from Sloan. So these are, to some extent, unobscured quasars. It's a rather heterogeneous sample in the sense that though many of them are optically selected, we also have some from radio and X-ray surveys. And from this sample, we have about 40 jetted or radio loud type objects, and we have about 84 non-jetted, i.e. radio quiet objects. So the redshift distribution is shown here. You can see there's about an average mean redshift of about 2, and the objects tend to be unresolved in, say, observations with Herschel. So we've combined the far infrared information we get from Herschel with other wavelengths, such as with SCUBA, MAMBO, and the VLA. And with that, we can fit the spectral energy distribution of these objects. And what this gives us is a measurement of the far infrared luminosity, which is a proxy for star formation in these objects. But also we, in some cases, also detect radio emission, which allow us to compare the radio emission via the radio far infrared correlation. So we can determine if both the radio emission and the far infrared emission are consistent with star formation. So some of these objects are quite simple. So this is an object, although it has quite a high dust temperature, you can measure its properties reasonably well. Some of them have double bumps. They have more than one dust bump. So there's probably an element of star formation and an element of AGN heating in such objects. Some of them we only have limited data. So our limits are on the properties in the far infrared are quite limited. And then there's some objects where we don't see any evidence of heated dust, but instead these are just blazar type systems. There's only a handful of objects from our sample in this regime. So what we find from our observations of 104 quasars is that 66 show evidence of heated dust emission. Actually, with follow-up observation of ALMA for some of the objects that we haven't detected, our detection rate is actually close to 80 or 90%. About 51% of them have median dust temperatures of about 40 Kelvin, which is typical of DFGs, dusty star forming galaxies, and about 90% have medium star formation rates of about 120 solar masses per year. But that's actually somewhat lower than what we typically get for dusty star forming galaxies. So here you can see the distribution of our dust temperatures from a model fits. And in this other plot, we're showing the dust temperature as a function of the far infrared luminosity. And what we find is that for our lens quasar sample, which are shown in the circles, and also when we compare with a sample of dusty star forming galaxies that's at redshift 2, we see that the far infrared luminosity and the dust temperatures are somewhat consistent, which makes us think that most of this emission is actually coming from star formation. Here we have the estimate of what those star formation rates are. So here we have the far infrared luminosity as a function of redshift. This is our detection limit with Herschel. But because the lensing magnifies our objects, we actually are probing a lower far infrared luminosity and therefore low star formation rate. So you can see here that our star formation rates are much, much lower than the typical dusty star forming galaxies that are seen at a similar redshift. Although we do have some objects which are clearly AGN and have composite AGN and star forming galaxies. But the question we often get is the dust actually being heated by the AGN? So we've done follow-up ALMA observations of about 7 targets. And we find that to look at the structure of the heated dust. This is the data shown here. This is some CO emission as well we detect from these objects. And what we find is the sizes of these objects can be divided into 2 regimes. One is where they have an effective radius of about 2 kiloparsecs, which is similar to DFGs, and star formation rate densities of order of around about 3 solar masses per year per kiloparsec squared. But we also have some extremely compact high star forming galaxies in our sample, where the effective radius is much smaller. It's sort of about half a kiloparsec. And here the star formation rate densities are much, much higher, of order 400 to 450 solar mass per year per kiloparsec. So in some of these cases, you're in the editing limited star formation regime. We've also tried, again, although they're compact, could it be that that therefore means the dust is very close to the AGN? Well, we've tried to separate the AGN and the star forming components by comparing the dust temperature and the far infrared luminosity and invoking a modified Stefan-Boltzmann relation. So here we have the effective radius shown in color, and then these are tracts of effective radius for a given far infrared luminosity and dust temperature. So here you're just assuming that the radiation is being heated isotropically, and it's given by 4 pi, the effective radius squared, multiplied by the Stefan-Boltzmann constant, multiplied by the temperature to the power 4. And what we find is that most of these objects, these are lens quasars in circles here, most of the lensed objects seem to be consistent with the Stefan-Boltzmann distribution, the Stefan-Boltzmann relation, I should say, which we think means that they're probably consistent with star formation. We do have a couple of objects which are above where they should be. So you can see here their effective radius is a lot higher. for their luminosity and dust temperature. But we also, so these objects might have evidence of heating from AGN, although they also do have clumpy star forming as opposed to some isotropic star formation distribution within them. So overall, we think these objects are mainly being heated. The star formation that the heated dust that we're seeing is mainly coming from star formation. So how can low frequency radio observations help us? Well, ideally, we would love to measure the star formation rates using the far infrared luminosities of all these lens quasars, but we only have a limited sky area from which we can do that. However, with sensitive radio surveys like LOTS that's being carried out with LOFAR, which is now observed around 6,000 square degrees in the sky, we can infer what the star formation rates are from the radio far infrared correlation. So here are some examples of data that has come from the LOTS survey at 6 arcsecond angular resolution. There are 63 lens quasars in the LOTS footprint, of which 42 are detected greater than 3 sigma. If we plot for the objects for which we have both radio and far infrared measurements and redshifts, we find that about 8 of them have a radio excess, as we say, so their radio luminosity is higher than we would expect given their far infrared luminosity. And about 11 of them are consistent with the radio far infrared correlation. And here, these tracks are just showing you what the radio far infrared correlation is if you evolve it to higher redshift. This is from Callisto Riviera. And we also have the far infrared radio correlation at lower redshift that was determined by Lingyu Wang. So from this, we can say, well, how many of these objects are actually related to star formation, and how much star formation is going on. So this is assuming that the radio far infrared correlation, we can use the radio far infrared correlation to do this. There is a caveat in that the radio derived star formation rates could, of course, even though we have objects which are on the radio far infrared correlation, we find that from high resolution centimeter VLBI, that in fact they're not just diffuse star forming galaxies, but actually these have compact AGN components. And this is an example of one of our objects which lies on the radio far infrared correlation and it has these radio jets. This is the black cross here shows the position of the black hole, whereas the red and the green show what we think are the jets that are coming from this object. Something I just wanted to mention is that the radio spectrum of this object is also quite flat. So you would think that it's consistent with an optically thick radio source. So it all seems to add up. However, when we take the 140 megahertz flux into account, we actually find this object has a steep spectrum component as well. So even though this object sits in the radio far infrared correlation, but it has significant VLBI structure, it may well be that the low frequency emission is uniquely tracing the star formation from this object.
So it's 1.5 minutes, Alan.
Sorry?
1.5 minutes?
1.5 minutes. Okay, thanks a lot. Okay, so I'll just skip to the end here. So we have two of the objects actually in our sample are extremely highly magnified. These are magnified by cluster lenses, and the two objects are SDS 1004 and SDS 2022 at redshift 1.7 and 2.8. The one on the left is the most interesting, so I'll concentrate on that. So the red contours are showing the LOFAR LOTS emission. The magnification of this object is 67. This means that it actually has an intrinsic 144 megahertz flux density of 13 microjansky, or an equivalent RMS of 2.5 microjansky per beam. So this is significantly deeper than what can be done with our LOFAR deep fields currently. The rest frame radioluminosity is of order 10 to the 23.2 watts per hertz. And if you assume all of this is due to star formation, we think this type of object has a star formation rate of about 5.5 solar masses per year. And what we're finding is that these objects, this particular object is, the noise limit is well below what we expect for the LOFAR confusion limit is 6 arc seconds, which is about 10 microjanskys per beam. So what we're seeing here is the objects which really lie under even the resolution that LOFAR can provide with the Dutch array. But this is the type of object we'd like to detect in the future with the long baselines. And Leo Morabito will talk about how we're using the LOFAR long baselines to try and probe these type of sources. One thing I would note though, is this actually such a low star formation rate galaxy? Well, it's kind of hard to tell just from these data at the moment. We're doing some VLBI follow-up to try and understand that. But what we do know is that it's been detected at 5 gigahertz, and the spectral index, similar to the object I showed before, is actually quite flat. is of order about 0.46. So we're not sure if this is just an optically thick AGN, or whether or not the high frequency VLA observations are just probing the AGN component. Just as a sort of final slide, well, is the star formation rate really so low? Well, we've looked at the radio loudness parameter of this object, and we find that it has an R or Li band over, the radio luminosity at 140 megahertz over its I band luminosity. And what we find is that it's got quite a high R value relative to the objects that have been typically observed, or the limits to the objects that have been typically observed previously with LOFAR. So this suggests that there might actually be jets associated with this object, and it might not have such a low star formation rate as we've measured. One thing I would say, though, as a huge caveat, is that this object is also quite variable in the optical, both intrinsically and also due to microlensing, which may affect its I band luminosity. So we're still looking into this to see if this R radio loudness value of about 3 is accurate or not. So I'll skip this, which is on feedback, but if anyone wants to ask me, I can do. You can do. So in summary, lensing can be used to probe these very faint radio sources and provide high resolution imaging to separate AGN and star formation processes. The wide sky area sensitivity and angular resolution we have from LOTS is ideal for detecting this weak radio emission from gravitational lens quasars. We have about a detection rate of 2 and 3 so far. The combined radio at low frequency and high frequency millimeter data suggests that these objects have forming stars at the order of about 120 solar masses per year. And there's also evidence of compaction in some of them, and about 50% of the ones we've looked at. And I would say this is consistent with what we expect from galaxy formation models, where these dusty star forming galaxies are created through mergers, and then they transfer into obscure quasars before evolving into passive elliptical galaxies. But currently we're doing higher angular resolution observations of some of these objects with LOFAR, but also with centimeter VLBI to really confirm some of these results. So I'll stop there. Thank you.
Thank you, John. We can probably have a very quick question before we move to the next one. Anybody in the audience? You can also raise hands. Okay, otherwise then let's continue the discussion in the Slack channel. Thank you, John, again. Our next speaker is Anna Ertzeg. Anna will speak to us about Faraday tomography with LOFAR. Anna, please go ahead. You have 17 minutes, and I'll give you an alert at the end of 15 minutes.
Okay, thank you. Do you see the presentation?
Yes, everything is good.
Just the presentation, right?
Yes, yes,
okay.
It's fine.
Thank you. So hello, everyone. My name is Anna Ertzeg, and I am a PhD student of Marijke Haverkorn and Wibo Jelic at the Radboud University Nijmegen, working at Ruđer Bošković Institute in Zagreb, Croatia. I would like to thank the organizers for giving me this opportunity to present to you my work on Faraday tomography of the LOTS data. And in this talk today, I will be showing you a huge mosaic of LOFAR 2-meter sky survey data that we created. And I will show you the statistical analysis we did on it and tell you about some things we learned along the way. So this mosaic was made to study the properties of magneto-ionic medium in our galaxy. As I said, the data we used is from the LOFAR 2-meter sky survey. Specifically, we use the very low resolution, so for arc minutes resolution, Stokes Q and U cubes, because we are interested in polarized emission. The LOFAR 2-meter sky survey is a northern sky survey at low frequencies of around 150 megahertz. And the data we use comes from data release 2, which has not been made public yet, but it is superior to data release 1 in terms of calibration, which allowed us to create a mosaic of really high quality. The area that we covered is covered by 440 pointings from this survey, each of which has a primary beam radius of 4 degrees. And these circles on the coverage image you see are those pointings with radius of the primary beam. The area we covered that way is the wider area of Heddeck's field, covering 502,000 square degrees, which makes this mosaic the biggest mosaic of low frequency polarization sky that has been made up to date. So with, yes, another thing I wanted to say here is that these red circles denote bad data that was not of high enough quality and that we excluded from this mosaic. They will also be marked red in some of the images that I will show you. Yes, and with this data, we performed Faraday tomography. So as Chris already spoke a bit about RM synthesis, which is a means to performing Faraday tomography, I will not be going into details here, but I will just say that Faraday tomography can help us disentangle the radiation by the amount of rotation it has been subjected to during its passage through the interstellar medium. And the amount of that rotation can be expressed in terms of the quantity of Faraday depth that is given in this equation, and it is proportional to some properties of the interstellar medium the radiation passes through, specifically the free electron density and the parallel component of the magnetic field. This quantity can be either positive or negative, depending whether the parallel component of the magnetic field is pointing towards us or away from us. Another important term I would like to introduce here is Faraday thickness. And that is because it will be very important for understanding the results and discussion I will show you. Basically, when we perform Faraday tomography, we are limited in terms of resolution by the rotation measure spread function. In its basis, the rotation measure spread function is very similar to the point spread functions that I'm sure a lot of you are familiar with. Basically, what it shows you is how would a source found at a single Faraday depth look like if we observed it and then retrieved it by the same procedure we used on our data. The width of this RMSF function defines our resolution. So if we are trying to see a structure that is in Faraday space of similar width than like our resolution, we will be able to resolve it and to see it. But if we try to see a structure that is much wider, so covers a greater span in Faraday depths than our resolution, we won't be able to see it, only the edges as small peaks, as you can see on the right-hand side of this image. And that structure is called then Faraday thick structure. So this effect depends on frequency. So if a structure is Faraday thick and therefore practically invisible to LOFAR and the lot survey, it doesn't mean that it will be Faraday thick and invisible for some other surveys on higher frequencies. And we will come back again to this term in the discussion. Now I will finally show you some of the results we obtained. So this is a Stokes P cube along Faraday depths. It's a video that I will play, and the resolution that we have obtained here is 1 radian per meter square. We have done this from -30 to +30 radians per meter square in that range, because that was the only range where we had emission, and the noise level reached here is 70 microjansky. So the video is starting. You can see the emission first forming at the topmost part and then spreading in all directions. And then if you can see my pointer, at positive Faraday depth, there is a different structure forming here. Once more in this area here. And then after that, we don't really see any more emission in this cube. This result can be also, so this 3-dimensional cube can also be collapsed to a 2-dimensional cube. We can do that, but by looking at a single line of sight, so along the Faraday spectrum, we take the peak value, the intensity of it, and we save it. And then we also look at where this peak appears in Faraday depth, and we save that information as color. Doing that, we get this beautiful image. where the intensity shows the peak intensity for each line of sight, and the color denotes the Faraday range in which that peak appears. The Faraday ranges are given below in the color bar. So here you can see that this spreading that we saw in the video is seen as gradients of colors, gradients in Faraday depths, of course, spreading in all the, oriented in all the different directions in this image. And maybe not so well yet, but you can see that there is a lot of structure here, a lot of like scratches and striations covering a huge part of this mosaic, of this field. And a very interesting thing can be seen if we go from right ascension and declination in this image to galactic coordinates. And this is, so the same image in galactic coordinates, we can see that these scratches really form a loop-like feature. And what we know is that in this area, specifically here, a object called radial loop 3 has been discovered by previous surveys. And since what we see is basically the diffuse emission and it's sitting on top of this loop, it seems that it is highly likely that these two structures really are in a way connected. So to take a better look at the structure of this image, we will just turn this image, remove all the colors, so turn this image black and white, like this. And now you can more clearly really see the structure of this loop. And you can see these scratches spreading over tens of degrees. So if we zoom in on this part here, we can see that not only do we have these very long scratches, we also have these much smaller and thinner striations, mostly perpendicular to the edge of this the loop, but also in many other directions. And this clearly shows the multi-scale nature of this data that we are working it. So of course, there is a lot of work that can be done here. But what we wanted to do first is actually compare this data and these results to surveys on higher frequencies. And we did that using spectral moments. So spectral moments are a very similar thing to collapsing that three-dimensional cube into a two-dimensional image, but they don't just take out the peak value, they take into account all of the peaks that can be found along the Faraday spectrum. So that is their advantage as opposed to the other approach. And so what we did here, we wanted to calculate these spectral moments, and we did that largely following Dickey et al. Paper from 2019, where the authors calculated these moments for the RAO survey and for the PARCS survey. We are here interested mostly in the RAO survey since it is a survey of the northern sky and it really covers the same area that LOTS does. And it is at higher frequencies of 1.4 gigahertz, which would mean that structures that are Faraday thick for lower frequencies and therefore are not visible in LOTS field will be visible in the RAO survey. Now I will go through the moments we made and compare them one by one with the DRAO moments and give you the conclusions. So first of all, we have the zeroth moment, which is basically the total polarized intensity integrated over the full Faraday depth spectrum. You can see this image is very similar to the one I showed you before, the maximum intensity. It shows the loop structure, and the most differences here are in the areas where we have multiple peaks along the spectrum. And comparing this to the DRAO moment here at the bottom, we can, when we overlap them, we really do see stretches of the loops of the loop, continuing from lots going through DRAO, and we really do see signs of loop being there in DRAO data. Specifically, that happens in this region, where in lots we have lower than average in the loop intensity. And this is the only place in DRAO where we do have emission. And this would basically imply that this part of the loop is for lots frequencies Faraday thick, and therefore we cannot see it, but DRAO picks it up. Further evidence that the loop is visible in this area of DRAO data comes from the first moment. So the first moment, given here, is the intensity weighted mean of Faraday depth along the Faraday spectrum. And here you can see that in the area of the loop, it is mainly negative, meaning that the magnetic field is pointing away from us. And in the other parts of the sky, it's mainly positive. Now, comparing that to the DRAO results, we see that in this area where we got indications there is a loop there in DRAO, we see that the values for Faraday depth are comparable. Keep in mind that, take a look at the scale. So in lots, scale is from -10 to 10, and DRAO is from -30 to +30. So the color is a bit different, but the values are very similar in these two cases. But then again, looking at this other side, we don't see the same thing in DRAO. So this leads us to conclude that this part of the loop connected emission is actually Faraday thin, and therefore DRAO doesn't have a high enough, sufficiently high resolution to see it. Another thing that we can take a look at, since we are looking at the first moment, is the galactic Faraday sky. This is a map based on Huchenreuter et al. And this is basically a map of Faraday depth along the whole galaxy derived from the extragalactic sources. And here, so it takes on the whole volume of the galaxy. So in this area, again, we see indications that the loop could be visible in this area. It's again, comparable negative values. But we also see some kind of a blob here that is not visible in lots or DRAO. So this first, the indication that seeing the loop in the full galactic Faraday sky is that basically the emission from this loop is so strong and so dominant along that line of sight that it is really visible when looking at the whole galaxy. And moving on to
2 minutes alert
moment. Thank you. Moving on to the second moment here. This is a new information that we have. It is basically the spread of the spectrum. So low values would give us a spectrum that is very narrow. For example, you can see that here a loop is not very prominent, which basically means that there is a one single dominant component of the loop that is narrow, and we see only that. And these areas where you have high values that are white are basically where the spectrum is wide. So this can happen in two ways. Since it is intensity weighted, you would even either have to have several structures of Faraday's spectrum of comparable intensity that are not in any way connected, just in the same like space in projection, same area, or you could have a Faraday thick structure, so the one that shows two peaks, and they would be of similar intensity, which would also produce a wide spread. And these two scenarios cannot be disentangled only using the second moment, but for example, in this area here, taking a look over the cube, we realize that here we have two structures that are of significantly different morphology. And so we can conclude that this is not a Faraday thick structure, but these are just two different things that we see along the line of sight. And so of course, this needs some more analysis to see if we could really use it to pick up some Faraday thick structures here. that is it for what we did until now, but we have a lot of plans for the future, since this is a beautiful big data set on which we can do a lot of work. And our next plans are to do an in-depth multi-wavelength analysis comparison with magnetic fields and with the H1. Some of this work has already been done in the circled fields here by Jelic and Braco et al. And there is a lightning talk that has been posted by Luka Turic, where you can hear a bit more about this multi-wavelength analysis in these marked fields. Thank you for your attention. And this is the summary of my talk. I am ready for questions.
Thank you. That was fabulous, Anna. Let's move to the question and answer session. You can see there are a lot of comments. So, questions, comments from the audience?
I'm going to ask that. So, Anna, I really enjoyed the talk. That's phenomenal data, and you've done some amazing work there. Really fascinating stuff. And I'm not an expert here, so this might be a dumb question, but I was just wondering, and you kind of mentioned at the end, but maybe you've done it already. Have you compared this against H alpha maps of the galaxy and seeing any correlations across that and any interesting features?
Yeah, unfortunately, we haven't done that yet, but we are definitely planning to get into all the H1 data, because I mean, it's just really a huge amount of data, and we just need a bit more time to do everything we want to do with it.
No, that's cool. Thanks.
Any more comments, questions? Alec Thompson. Just a second, sorry for that. Yeah, you're good to go ahead.
Cool. Thanks for that. Hopefully you can hear me. No, this is all really amazing. I've got a bunch of questions, but I guess we can continue that later. My one for now is that given the low frequencies and the other correlations that have been found in the smaller fields are showing that, you know, the diffuse structures LOFAR are seeing are all nearby. Can you tell us what you think about what this states about the physical origin of loop 3 and where we think it might be?
We haven't really much done on the physical origin of the loop 3, but we are planning to do some work on the physical origin of the emission that we see, so in the loop 3. And this is something that was talked a bit about in a recent paper by Braco et al., talking about, does the emission that we see come from the neutral regions? So emission that we see in Faraday depth comes from the neutral region, or does it come from the Faraday rotating medium? So I think in that light, we could maybe answer some questions about the emission, the origin of the emission that we see.
All right, thank you, Anna, once again. And let's move to the last talk of this session, which is by Aditya Chowdhury. Aditya will discuss about high redshift neutral hydrogen studies. Aditya, please start sharing the screen. You have 17 minutes and give you an alert in 2 minutes.
Yes, thank you. You can see my screen and hear me fine, right?
Everything's fine.
Okay, thank you. So hi, I'm Aditya from the National Center for Radio Astrophysics in India. And so I'll talk to you today about atomic hydrogen and high redshift galaxies, specifically at redshifts of 1. And so this work is mostly done with Nassim Kanekar and Jairam Chenkalur. And here's the broad outline of the talk. So I'll give you an introduction and set up the context for the work. And then I'll talk to you and describe the upgraded GMRT 21 centimeter survey that we have been carrying out of the deep T fields. And then I'll talk to you about the results, which is the detection of H1 21 centimeter in emission at redshifts of 1 for the very first time. And then I'll talk to you about the implication of these results to the quenching of star formation at redshifts less than 1, tell you about our future plans and summarize. So I'll start with this plot here, which is a kind of what we have learned over the last 2 decades about the evolution of star formation rate density as a function of redshift or time. And what we have broadly understood from these measurements of the cosmic star formation rate density is the following: that if you trace the star formation rate density of the universe after the end of the epoch of reionization, you see that it steadily rises out to about redshifts of 1, and then flattens, and this flattening stays, flattens and peaks, and this peak stays for about a couple of gigayears, and then it declines steeply from redshifts of 1 out to redshifts of 0 over the next 8 gigayears. And so this peak is really crucial, and this is where 50% of the stellar mass that we observe in the universe today was assembled, and this is why this is known as the epoch of galaxy assembly. And what has remained puzzling for a long time now is that why is there this decline in the star formation rate density after the epoch of galaxy assembly? What happened to it? And a crucial a crucial measurement that is required to understand this dramatic fall in the star formation rate density is what is happening to gas in galaxies, because gas is finally what fuels the star formation. And so this is a fundamental parameter that you need to understand in order to understand what is happening to the star formation rate density. And as most of you would know, that atomic hydrogen is really the primary fuel for star formation. This gets converted into molecular hydrogen, which then gets converted to stars. And H1 also sort of dominates the interstellar medium of galaxies, of star-forming galaxies. And to understand this, you really need the 21 centimeter transition in emission, because the emission signal is expected to be optically thin, and it straight away gives you the total H1 mass of galaxies. But the problem with this emission is that it's weak. So although it has been studied to great details in nearby galaxies, you would have seen these spectacular maps of H1 and velocity fields and so on. But going to higher redshifts has been really a challenge. And so there have been these enormously large integrations with the Arecibo, the WSRT, the Jansky VLA, and the GMRT to really push 21 centimeter studies. But even this has been successful out to fairly lowish redshifts, from redshifts of 0.2 to 0.4. And the highest redshift detection we have today of the 21 centimeter emission from an individual galaxy is from the JVLA Chile survey, from their pilot 180 hours of data. And this is, and they managed to detect a fairly massive galaxy with mass 3 times 10 to the power 10 with so much of integration time. And to really push this to epochs where the star formation rate is doing very interesting things like the dramatic fall I showed you, and to understand what is happening there, you need enormous amount of time on the best telescopes today. You need more than 10,000 hours, and which is ridiculous and insane, to get individual detections of galaxies with H1 mass of 10 to the power 10 solar masses at redshifts of 1. And so to get around this, you can use this technique, which is stacking or co-adding the 21 centimeter emission. So essentially this technique gives you the average H1 mass of a sample of galaxies. And so the technique is fairly straightforward. What you need to do is you need to have a large number of galaxies in your field of view. And then all you do is you extract cubelets from these around these galaxies. And a really critical thing to do here is you need to know where the 21 centimeter emission is expected to lie. So you need to know very accurately that information, because you'll be aligning the spectra to the rest frame velocity before you sort of add them with stack them together. And so not only do you need spectroscopic redshifts, you need very good quality spectroscopic redshifts with velocity resolutions better than 100 kilometers per second. Otherwise, you'll simply smear out the signal. So the game here is simple. You get as many galaxies as possible with accurate redshifts in your field of view, and then you combine them, the noise goes down as square root of number of galaxies. And if you have sufficiently large number of galaxies, you'll see that the signal pops up both in the image plane here as well as in the spectral domain here. And so this technique has been used to get average H1 21 centimeter emission detections out to redshifts of 0.4. but pushing beyond that is really a challenge. And it turns out that the upgraded GMRT is an excellent instrument to push 21 centimeter emission studies via stacking experiments to higher redshifts into redshifts of 1 and even beyond. And um, and so what I'm showing here is the frequency coverage of the, so upgraded GMRT essentially has 4 bands right now. I'm showing you only the 3 higher frequency bands here, and the sensitivity of these bands and the redshift coverage for the 21 centimeter line. So the highest frequency band, the L band receiver, or band 5 as we call it, goes from about 980 megahertz all the way out to 1500 megahertz or so, and it covers the 21 centimeter line from the local universe all the way out to redshifts of 0.4. And then you have this band 4 system, which is 550 to about 830 megahertz or so, and this covers the redshifted 21 centimeter line from about redshifts of 0.7 to all the way to 1.5. And finally, you have these band 3 receivers, which is 250 to 500 megahertz, and you get you cover a redshift from 2 to 4. What I'll focus on in this talk is observations using band 4 receivers. So specifically observing galaxies for their 21 centimeter emission in the redshift range 0.74 to 1.45. And this really covers a crucial epoch of our universe. So you can see this band I have now plotted here. You can see that we cover a part of the peak of the epoch of galaxy assembly, and then the subsequent decline after redshifts of 1. And so this is where we expect a lot of, so this is where a lot of action is happening to the star formation rate density of the universe, and we really want to understand what is happening to the to H1 in galaxies at these redshifts. And for that, we observed the deep 2 fields using the band 4 receivers of the GMRT, and the deep 2 survey turns out to be just the perfect survey for such as H1 21 centimeter stacking experiment at these redshifts. So this is a survey which has gone very deep. This is 90 nights with the DMOS spectrograph on the Keck telescope, and it covers and it gives us redshifts in exactly the redshift range we want, 0.74 to 1.45, which is a redshift desert where getting redshifts is really difficult from ground-based telescopes. And you have exquisite spectroscopic redshifts for these galaxies with redshift accuracies of 55 kilometers per second and better in some cases. And so basically there are these 7 subfields with 28 arc-minute cross 42 arc-minute footprints. And what I've shown here is in red the GMRT primary beam at our frequencies. And you can see in color codes the galaxies that fall inside the GMRT primary beam, which we have used to of whose 21 centimeter spectra we have stacked. And here in the numbers show you the number of galaxies we cover in each of these pointings across the entire redshift range. So our full survey is 520 hours of UGMRT time with the band 4 receivers, and we cover these fields with 7 pointings as shown here. And what I'll focus on mostly here, except in the tail end of this talk, is results from the pilot 100 hours, which we had done in October, December 2018, and which got published recently. And we have 5 pointings. We did not observe field 2 in the pilot. We did 5 pointings on field 3 and field 4 with about 20 hours of total time per pointing. And here I'm showing you the UGMRT continuum maps. We have, depending on the kind of sources there are in the fields, we get to about 5 to 8 microjanskis per beam at about 650 megahertz. And we cover a total area of combining the 5 fields of about 1.2 square degrees. And now I've overlaid the deep 2 galaxies, the position of the deep 2 galaxies in the continuum maps. And finally, there are about 11,000 galaxies in combined. Finally, we picked 7,653 blue star forming galaxies for which we could obtain clean 21 centimeter spectra, which are not affected by RFI or systematics in the redshift range 0.74 to 1.45. And then we extracted 21 centimeter cubelets around the known redshift of each of these galaxies, and we stack them. And what you see here is the first detection of 21 centimeter emission at redshifts of 1. This is the highest redshift. Before this, the highest redshift we had got to was redshifts of 0.4. And on the left, what I've shown you here is the stacked 21 centimeter spectrum. And you can see a clear detection centered at 0 kilometers per second with a line width of about 270 kilometers per second. And on the right, I've shown you the velocity integrated signal, which just collapses these 3 channels in the image plane. And again, you see a clear detection at the center. And from this detection, we infer an average H1 mass of about 1.2 times 10 to the power 10 solar masses. And this is really comparable to the average stellar mass of the population, which is about 10 to the power 10 solar masses. And this is dramatically different from what we observe in the nearby universe. In the nearby universe, if you observe similar galaxies of similar stellar mass, you have about 40%, the H1 mass is about 40% of the stellar mass, whereas here it's comparable. And this is also similar to what observations of molecular hydrogen have found. So clearly there's more H1 to fuel the higher star formation, but is that really enough? And to understand that, one very simple parameter one can look at is the depletion time, which is simply the gas mass divided by the star formation rate. And it tells you how much, for how long, in a closed box scenario, how much time can the gas available sustain the star formation rate. And so this picture, simplest toy model you can construct of a galaxy is that there's a circumgalactic medium on the outskirts of the galaxy, and then there's H1 which goes out to further distance, and then H2 plus H1 inside, and then finally stars at the very center. And this also sort of traces the sequence that star formation proceeds, that is gas flows from the CGM to the ISM, and then cools to form H1, and then cools to form H2, and then finally form stars. So in just to illustrate what depletion timescale means, let's consider the local universe. So the H2 depletion timescale is found to about 1 gigayear. What this means is that if you had a system with only H2 and stars, you would quench galaxy star formation in the galaxy in about a 1 gigayear. The H1 depletion timescale in the local universe is much longer. It's 7.5 gigayears, which means that even if there is no gas flowing from the CGM into these galaxies, and if H1 to H2 is going fine, then you will have quenching in about 7 to 8 gigayears. What this means is that a galaxy in the local universe can sustain the star formation rate for 7 to 8 gigayears without fresh accretion of H1. And so availability of H1 is really not a bottleneck here. And what we want to understand is what is happening to galaxies at the epoch of galaxy assembly, where there is so much action in terms of the decline of the star formation rate density. And what we find is really interesting. So to get the depletion timescale, you also need the star formation rate density. And so we have continuum maps, which are really rest frame 1.4 gigahertz. So we simply use that to we stack the continuum emission of these galaxies and find the star formation rate. So we find an average star formation rate for these galaxies of about 8 solar masses per year. And combining this with our average MH1 measurement, we find the depletion timescale is about 1 to 2 gigayear, depending on whether you look at bright galaxies in our population or the full sample. And so really there is this dramatic fall in the depletion timescale from the local universe out to redshifts of 1. And this is also very similar to the H2 depletion timescale measured at these redshifts. And so what this is telling you is that if there's no accretion from the circumgalactic medium, you would have quenching in of star formation in 1 to 2 gigayears. And this is this fits in with the time scale in which you see the star formation rate density to decline, and sort of suggests that it's possible that if for some reason you did not have sufficient accretion of material of H1 in these galaxies, you would that could just well explain why star formation rate density falls below redshifts of 1. Now, more interestingly, our observations span a largest redshift range from 0.74 to 1.45, which in terms of amount of time is about 2.6 gigayears, which is larger than the depletion time we measure. So if we have enough sensitivity and we manage to break our measurements of the average H1 mass into 2 bins in redshift, And if there's no accretion, we should see hints of that. And here's where I'll present you preliminary results from our full survey. This is using the first 250 hours, which gets us just about sensitivity to do such an exercise. So what I show here is the, again,
Aditya, you have less than a minute, okay? You have less than a minute.
Yeah, thanks. So what I've shown here is the average 21 centimeter emission in two redshift bins, one going from 0.74 to 1.14, another 1.14 to 1.45. And you see that there's at best a tentative detection in the lower redshift bin, and the signal really jumps out in the higher redshift bin. And so if I now look at the ratio of MH1 to M star, you see this spectacular drop, which sort of coincides with the fall in the star formation rate density, and then it about stays flat out to the local universe. And this fall, like I said, if I show you the two bins in the star formation rate density plot, you can see that one of them is in the peak or the plateau region, another is covers the fall, and this is where you see this dramatic transition. So both the short depletion timescale and the rapid decrease in the average MH1 to M star tells you that there is probably insufficient accretion from the CGM, and this is why star formation rate falls. And one could speculate why that is happening. Is there a switching off of cold mode accretion? Is there feedback, which is really so dominant that it expels gas and does not permit more infall? And that brings me to few plans, what we hope to do in the coming 6 months or so. First of all, we will finish the full 520 hours, and this will tell us whether the fall we see in the MH1 to M star, it will confirm the fall, and our noise in the cubes goes down, has gone down a square root of n, which is the number of galaxy, which is great. And then what we will just start doing this month is we'll start observations using band 3, which will go out to even higher redshifts from 1.8 to 2.8. We'll observe in Cosmos for this. And you can see that combining these observations, we will really cover this very exciting epoch in our universe. And with the upgraded GMRT, we hope to understand what is happening to H1 in galaxies for the first time over a significant fraction of our universe, which is 11 giga-years. And with that, I'll stop and leave you with the summary slide and take any questions you might have.
Thank you. That was great work, Aditya. Move to the question and answer session. We could have probably a very quick one. Anybody wanting to raise their hands? There is nothing in the Q&A box. All right, if there are no questions to Aditya, please continue the discussion in the Slack forum. So we have come to the end of the session 7. Thanks to everyone who joined us from across the globe. There's a coffee tea session following this. Do join using the link. See you for the next session in about